Monday Night Calculus. My name is Curtis Brown, and I am joined once again by Steve Kokoska and Tom Dick. Really excited to have you guys all here with us this evening. I've got a couple of things. I know we're starting a little bit different than we normally do. I've got a slide up here. This is moving with polar and parametric equations. We're going to get right into that content really quickly. However, I wanted to just showcase a couple of things for you guys tonight and let you know about a couple of summer learning opportunities we have coming up this summer. So first of all, we have a summer learning opportunity that is going to be live in Houston, Texas, a little town called Pearland in the summer this summer. Information, I'll put a link out to that TI workshop information here in the chat in just a second. But we'll be running that date is June 3rd. Looks like it'd be a really exciting workshop there looking at the TI-Nspire CX2 CAS. We also have one for the TI-84 plus CE graphing calculator. Same time, same location there in Pearland. We'll just be running those side by side during the day on that June 3rd. So the registration and everything, I'll put those links in the chat really quickly. We also have one third thing that I want to make sure that you guys are aware of, and that is on July 21st, 23rd, 28th, and 30th. We have a virtual workshop that's going to kind of span those 4 days, a couple hours on each day. The the virtual workshop also includes the technology just like the other ones, but it's also a virtual equivalent of a in-person workshop. So I'll put the links to all of these things in the chat momentarily. Anyway, Steve, I think that concludes the quick little sales pitch I had for people to come and join us and learn a little bit more about calculus and about using the technology for success in those spaces. So I'll let you guys take it from here.
Okay, thanks, Curtis. I'm going to try to share my screen. And there we go. Great to be with
Fabulous.
you and Tom again tonight, Curtis. Thanks. It was nice seeing everybody in Dallas. We've got some great problems, I think, tonight on parametric equations and polar equations, particles moving in the plane. And for whatever reason, Curtis, most of these problems seems to lend themselves to a lot of technology usage. So Tom's got a lot of cool things with the TI-84.
That wasn't on purpose, was it, Steve?
No, it just seems to be that's the way these problems show up on the free response. They tend to be very technology active. I think one of the reasons is because some of these problems are extremely difficult to manufacture so that they work out by hand. Some of the definite integrals can be really difficult. Anyway, we're going to do a little bit of exploring. We're going to think a little bit about some of these to make sure that the technology has given us the right answers. I'll do a little bit with the TI-Nspire, and Tom will try to do I think we'll do some great stuff with the TI-84. So bear with me here, Curtis. I hope you've done your homework. We have a particle moving along a curve in the XY plane. Its
I have
position.
not done my homework. I'm
Oh
kind of like my
no,
son here.
Curtis.
He's done more of his homework than I have.
Well, the position is given by x of t, y of t, for t greater than or equal to 0, and there are the two functions here that I've given you right there. Before I get to answering part A, get to A and to answer it, I just want to remark that there's an awful lot of notation here in this kind of a problem. I've got x's and y's that are functions. When I go to the TI-Nspire, I've got an f and a g, and I've also got an x1 and a y1. So there's lots of functions floating around here. This is really important, I think, to keep all the notation and correct and communicate correctly. Let's see, before we even try to do this with technology, I wonder if there's anything that we can conclude about the nature of this curve. Let's just think about this a little bit. So what happens as t increases from 0? I'm going to take a look at x of t first. And Curtis, don't let me make a mistake on this one. As t increases, it seems to me, just thinking out loud, the sign of t I know is periodic. So that seems to me that this x of t is going to be going back and forth as the argument is periodic. Certainly arctan is going to be going back and forth. And maybe I could even think just a little bit. I know that the sine of t, let's see, would be periodic. The values would be between -1 and +1. So what does that mean about the arctan? Let's see, that means it must be going between what, -π/4 and +π/4. And I'm going to multiply that by that 2 out in front. So it kind of looks like that x of t, the x coordinate of this particle, its position, looks like it's going to go between -π/2 and +π/2, roughly what, a 1.57, a -1.57. Okay, what about y of t? Is there anything you can tell me about that? Well, I don't see anything that might be periodic there. But one thing you might think about here is what happens to this y coordinate as t increases without bound? Well, I'm going to give it a try. Curtis, can you see on that one? What happens as t increases without bound to that y coordinate of the particle? Can you tell? Well, I can't hear you, but I think you're telling me something.
I was trying to.
Okay.
I promise I really was trying to
Okay. What do you think?
respond. So as t increases without bound, it looks like that y particle is going to trend towards zero.
It certainly does. Very good. So it kind of looks like we have x going back and forth between the value of x going back and forth between -π/2 and +π/2. And the y coordinate is going to be getting closer and closer to zero. So we might use that information, that initial sort of understanding of the path, to make sure that the technology kind of backs that up. So I want to sketch the path of the particle, and here's how I did that on the TI-Nspire. The first thing I did is I defined this function f and this function g to be my x of t and y of t. And then on the TI-Nspire, I can actually input these curves, this curve parametrically. So I went into parametric mode and I typed in x1 of t is just f, y1 of t is g, and I plotted this curve. And that's what it looked like from 0 to about, oh, jeepers, I've forgotten now. I think to around 4 or 5 for t equal to 4 or 5. But Tom will back me up on that when he works with the TI-84. So that's what it looks like. I can, for this limited value of t, I can kind of see how x is going back and forth. I can kind of see that -π/2 and that +π/2. And I can also see that as y increases at least a little, the y coordinate is getting closer to zero. Pretty cool. Now it says up here to use arrows to indicate the direction of the particle. So I wanted to think about that just a little bit. That's why I did a few calculations down here at the bottom. It's not too hard to see that the particle starts out at the origin. If I plug in a t equals 0 up here, I get a 0. And a t equals 0 there, well, let's see. The sine of 0 is 0. Arctan of 0 is 0. So, okay, it certainly starts at the origin. And just to sort of double check, just to make sure I've got things correct here, I found x of 1 and y of 1. And I don't know, I'm going to try to kind of quickly plot that on my curve. I think that's going to be, let's see, 1.4, roughly 1.5. I think it's around here. So I believe the direction of motion of this particle is like that. That's pretty cool. So, at least in my opinion, there's an awful lot to think about here. We don't want to blindly accept what the technology gives us. It seems to back up what I thought about, what I could see as I analyzed those functions, well, conceptually. Cool. Let's take a look at B. Find the velocity vector and the acceleration vector at time t equal 2. Tom will have to back me up on this, but I think this is a pretty common question on the free response portion of the exam, of course, for the BC students. And it's really just knowing how to find the velocity vector and the acceleration vector, knowing conceptually what those vectors are, and then going directly to the technology to get an answer. So I'm going to kind of go back and forth between my screen illustrations and my answers down here. So I have to find the velocity vector at 2. All right, so that means I have to find x prime of 2 and y prime of 2. That's the definition of this velocity vector at 2. So I'm going to go to my calculator. I'm going to take the derivative of f and plug in 2, derivative of g and plug in 2. I got a minus 0.456 and a minus 0.360, and there we go. Beautiful. Now, before I find the acceleration vector, I wanted to talk a little bit about notation here. A couple of little things seem to come up frequently. You'll notice that when I wrote this, I used, I think, what is some common notation for a vector, and that is what are called, I believe, angled brackets. But Tom, I think, correct me on this, when we grade these for students, we're not too picky about those brackets, about those angled brackets. I mean, we'll almost take parentheses there. And we will often accept this too. If a student just reports x prime of 2 is equal to minus 0.456 and y prime of 2 is minus 0.360. Frequently, that will be accepted too for the velocity vector. Now, I don't know what Sharon's going to rule this year. I mean, there is sort of this movement towards even greater precision in presenting your answer. But in the past, we've accepted that.
Yeah, I think that's correct, Steve.
Okay. One thing we do want to make students aware of, and teachers, of course, is when you're reporting this velocity vector, you do not want to say, and I'll erase this here in a minute, you don't want to say something like this: v of t is equal to minus 0.456 and minus 0.360. That's equating a function with a specific value. And in the past couple of years, the chief reader has been very, very particular about this. We don't want to equate this function with a specific value. Okay, so that would not get credit. Beautiful. I want to find the acceleration vector. One more thing, Tom. What do you think about this? If a student were to find the velocity vector, before I go to A here, if they did not include that step, but just went directly here without explicitly saying how they found those two values, unclear to me whether or not they would receive full credit. I think there's got to be some indication about where those numbers came from. So I think it's important to say it's x prime of 2, y prime of 2, not x prime of t, y prime of t, but x prime of 2, y prime of 2. So there's not much analytical stuff to write down here, but you do have to be precise with the notation.
Yeah.
So to find the acceleration vector, that's a of 2. That's going to be x double prime of 2, y double prime of 2. I went to my TI-Nspire. I can find the second derivative directly. That's a little bit different than the way it's done on the 84, and Tom will show you that in a moment or two. But I found those two values and reported my vector. So I guess the bottom line is here in this kind of a problem. I'm going to see if I can erase that. Hey, did it work? Hey, how about that? So in this kind of a problem, if I just wrote that down right there, I believe you would receive full credit. You would earn full credit for this part. So you've written the correct mathematical notation, you've written the correct mathematical statement that you've used now to go to your calculator, use the technology, and you've written the answer correct to 3 decimal places. And just a reminder again, I set my calculator to fix 3 so that I get 3 decimal places on the screen. So I don't have to worry about rounding or truncating or any of that by hand. It's rounded for me on the screen. But remember, I can store that to a greater degree of accuracy if necessary. Terrific. Down towards the bottom here, find the speed of the particle at time t equal to 3. Well, again, I'll kind of go back and forth between the screen illustration and the mathematical statement. To find the speed at 3, I actually have to find the absolute value of the velocity at 3. There's the expression. Again, with the 3 in there, not a t, that's x prime of 3 squared plus y prime of 3 squared. And I've got to take the square root of that. And I think when I went to my calculator, I got a 1.956. Look, this notation is a little cumbersome here, and I get it. It's a little tricky. You just have to be careful in inputting all of the correct parts there. Take the derivative of my function f with respect to t, evaluate that at t equals 3, and then square the whole thing. Do the same thing for g, and finally add them up and take a square root. And by the way, there is certainly no harm in doing this in steps. I did it all in one step, but you could do this in a couple of steps, 3 or 4 steps if you wanted to. Fantastic.
Steve, I would just interject here that I know I like to tell my students that this is a really completely consistent use of those the symbols that look like absolute value,
Yes.
because it's denoting the magnitude of that vector. And in one dimension, the magnitude is of a real number. One-dimensional vector is its absolute value. And so
Right.
we're just staying consistent with that.
Yeah. Okay. Very good. I think I've got a part D here. Find an equation of the tangent line to the path of the particle at time t equal 2. Again, I think another very common question on the free response portion of the exam for the BC students. So I'm going to find the equation of the tangent line. That means I need a point and a slope. So here's my point. I'm sorry I did not show this with a screen illustration, but I found x of 2 and y of 2. That was my function f and my function g. So my point on the curve, I think, is a 1.476 and a 1.2. And I'm sorry, I'm going to sneak over here to the right-hand side in my screen illustration. It's right there on the curve. And I tried to, I added some notation in my screen illustration for that. In order to find the slope of the tangent line, that's y prime of 2 divided by x prime of 2, and no other alternative here. I don't want to try to do this, of course, analytically. This is a calculator active question. I'm going to go directly to my TI-Nspire, and I'm going to find that slope. There's the derivative of y at 2. There's the derivative of x at 2. And the slope is therefore 0.790. Tom and I usually or often get asked this question, well, wait a minute, if that third decimal digit is a 0, do you have to include it when you write it? No, of course you don't. You can just say 0.79. You don't even need the 0 out in front if you don't want to. We usually write it there for completeness, but you don't have to write that. So here's an equation of the tangent line. It's y minus y1 is equal to the slope times x minus x1. And look, unless otherwise asked for, you can certainly leave the equation of the tangent line like that. That's perfectly acceptable. You know that I'm not satisfied with that, Curtis. I wanted some graphical evidence of that. So over here on the right-hand side, again, you can see my curve. I'm going to put in a couple of arrows again just to remind myself. My particle is moving along that curve. And I think if you can see the colors, maybe, the curve is either in black or dark blue. And my tangent line right here is in green. And it looks right. It does, in fact, look like it's tangent to the curve at that point. I feel pretty good about that. I think I got the right answer. I'm feeling good about that one. And E. You can kind of see now, Curtis, why this kind of a problem is lends itself more to a calculator active question. Jeepers, trying to figure out this kind of a definite integral would be very difficult with a square root in there. It'd really have to, the functions would really have to work out nicely in order to get this one analytically. So find the distance traveled by the particle over this time interval 0 to 4. I just have to, again, go directly to the formula. It's the definite integral from 0 to 4 of the square root of x prime of t squared plus y prime of t squared dt. Again, make sure when you're writing this step mathematically that you have a 2 in there, pardon me, a t in there, and not a number, not a specific value like a 4 or like a 2. And I'm going to go directly to my calculator here and get this answer. And again, a little cumbersome to write that notation. Take your time. I've got my functions f and g already entered in my Nspire. I'm going to take my time and make sure I've got the correct symbol for the derivative of f with respect to t, square it. Add the derivative of g with respect to t and square it. Add them all underneath the square root. I've got my dt on the end, and it looks kind of funny, but my answer is up here on that line. There it is. It's 5.371. That's kind of cool. Wow. Thanks for putting up with all of that, Tom. You got a little technology on the 84?
Sure. Yeah.
Okay.
Go ahead.
All right. All yours. Okay. There we go.
Okay. So hopefully I'm sharing my TI-84 screen with you all. See that. And just kind of first basics with parametric. This is going to be one of those places in the calculus course where we'll actually change the mode. I would say 90% of the time you're going to be in function mode. When you go to y equals, you see your usual y1 equals, y2 equals, and so forth. But we want to get into a parametric graphing mode. And so to do that, I'm going to press the mode key. And you can see it's down there on the 5th line. You see function is highlighted. I'm going to use my right arrow key, get it flashing on parametric, hit enter. And now I'm going to return to the y equals. And I can see it looks very different now. Okay, now it's set up for parametric equations. So there's a pair, an x1t, y1 of t, for each individual graph. And so while I'm here, why don't I just go ahead and enter in the one that we're working with on this problem. So that was 2 times the inverse tangent of sine of t. Let's see, do I need to hunt down the t? Well, when you're in parametric mode, this handy key up here says x comma t comma theta comma n. It changes depending on what the dominant independent variable is. When we're in parametric, t is that independent variable. So I'm going to press that xt theta key, and you can see it brings up a t for me. All right, so that's my x1 of t. And now for the y1 of t, let's see, let's get a fraction. Little template there. I'll put in 3 times t in the numerator. And the quantity t squared plus 1 downstairs there in the denominator. I think we've
Pretty cool.
got it entered correctly here. But before I dive into a graph, let's go over to the window key and check that out, because that's going to look a little different too. We have our usual x min, x max, y min, y max. Those set us the dimensions of our viewing window. But the thing is, we have this third variable, t, the independent variable, and we need to set a range for it, or a domain, that would be a better word for it, at least for graphing purposes. Now, I think in the problem, there wasn't really any upper bound on t. It just said for t greater than or equal to 0. So t min equal to 0 is still a good starting value. In some sense, the t max is going to be kind of arbitrary. Without knowing better, Steve, I'm just going to try 5.
Yeah, good.
We'll see how that looks.
Okay.
Maybe that we may need to go back and adjust this to get more graph if we need to. The t step, that looks really weird. But I don't know if you notice that t max look like 2 pi in decimal form. I think this is some multiple of pi here, most likely. I'm going to try, I'll tell you what, I'm going to try 0.1, see what that looks like. You can make that t step anything you care to. And well, let's give this a shot, see what kind of graph we get from this. So I'm going to go ahead and hit graph. And I think I'm on the right path here, except we didn't get nearly as much of the graph as you did. You had another good leg here. So I'm going to go back to my window and do a couple of things. I'm going to change that Tmax to 10.
Yep, that sounds good.
And, you know, while I'm here, I'm going to get a little bit bigger picture by cutting the X-min and X-max in half, I think. So what I'm going to do is make it negative 3.3 to positive 3.3. And I'll do the same on the Y-min and Y-max. I think that'll work. Fit in nice.
Yep.
So I'll make it negative 2.05. And if you're wondering why I'm being so particular about making the window like exactly a half of what it was before, it's because what I had before was nice and squared up, and this will maintain that kind of square scaling that I had before. All right, let's give this a shot.
Hey, that's pretty good.
This one actually has a little bit more than Steve's did. So we can see it, but Steve's initial analysis, he said the X coordinate would be kind of bouncing back and forth between minus pi over 2 and positive pi over 2. Simultaneously, the Y coordinate would keep getting closer and closer to 0. So if we plotted a lot more of this, I would suspect that this line would keep bouncing back and forth horizontally, but it would always be above the x-axis. It would become squeezed. It would get like more and more squeezed down like an accordion or something. When I turn on the trace, I'm actually, okay, I'm going to see my pair of function values, or at least most of them. You know, it's this, one of these function formulas was long enough. We see it's truncated. But notice down at the bottom, I actually get 3 values. It's reporting me my X and Y coordinates, but it's also recording the T coordinate. And if we're thinking that as, and we often do with parametric, we often think of T as representing time. And so this is the path of some particle moving with respect to time. And so when I start hitting my right arrow key, it's going to advance in T value, but also show me my position on that curve. So I'm going to go ahead and well, I can jump to any value, just like I can do with trace on a Y. Excuse me, my usual Y equals function grapher. I'm going to jump to T equals 2. Oh, it didn't jump very far, so this thing really kind of slowed down, it seemed like. And I'm remembering that Steve calculated a velocity here. And I think your velocity vector, it was negative in both coordinates.
That is correct.
So what would that tell me about the motion of the particle at this time? Well, if the X velocity is negative, that means it must be moving to the left. The X derivative is going to give me left-right direction. So a negative X derivative is going to be moving to the left. A negative Y derivative means moving down. So this thing should be heading on a kind of left-down path. And you can see that looks exactly right. In fact, if I start incrementing, we should see it going down and to the left. And we can see that's, so I'm just doing a reality check. This is actually checking out. So that's neat. Okay. Let's see, for calculations like velocity, you can just, if you quit to your calculator screen, we can do our usual math like this. So if I pull up the math menu and I want to do a derivative, I'll go down to number 8. Oops, overshot. There we go. Numerical derivative. I'm going to take the derivative with respect to t, and then I can call up the parametric function x1 of t. And let's see, this was that time, was it t equals, I'm just referring to my notes here. Oh, it was still at t equals 2, is that correct? Yeah. Where we
Yes.
wanted the slope of the tangent line. So let me put a 2 in there. There it is. Okay, and that's, I think, the value that Steve got. Very close to it. And let's do the same for the y component of velocity. So I'll do math again, pull up my numerical derivative with respect to t, go to my parametric variables, and get the y1 of t, also at 2. And there we go. Yep, and that looks like it's matching up nicely. If I wanted dy dx, well, then I can take this dy dt value that I just got. Excuse me, let me do a last answer. Or I'll do it this way so it's a little more visual. I'm just going to scroll up and copy that, enter it, and then divide by, scroll up to that dx dt value, copy that down. So now I'm doing that division, and there's that slope that Steve got. Okay. Now on the Nspire, Steve actually plotted the tangent line. And to get that, he needed those two coordinates, that are x1 of t of 2, y2 of t, that we could see on the trace thing. We could call those up here. But to graph that on the Nspire, Steve was able to just move over to his F1, F2 menu, put the equation of the line in there, and graph it right on top of the parametric. On the 84, you're either in function graphing mode or parametric mode or polar mode, some specific graphing mode. So if you wanted to do a graph of the tangent line in parametric, let me just show you how we could do that. I'm going to go back to y equals. What we'll need to do is just plot that line, but use the parametric plotter to do it. Now, if you're just plotting a function, it couldn't be simpler to plot it parametrically. All you need to do, okay, so I'm going to use x2, y2 for my tangent line, is I'll just make the x2 of t equal to just plain old t. And then I'll make y2 of t equal to the tangent line equation. And so I will cheat here and use what Steve came up with there. We had, let's see, it was 0.79, I think.
Yeah. Yep.
Times the quantity. Now I'll use t instead of x for because notice my x2t is t. Okay, so this is my x variable, t minus 1.476. Close that off, and then we'll add on the 1.2, I think. So let's see, add on 1.2. And let's go ahead and graph that, see what happens. Boom, there we go. Good. And it looks nice and tangent at that point. You may be looking at this line and saying, well, it actually works pretty well for where the point of tangency is, but we only have the graph in the first quadrant. What's going on there? Well, we go back to our window. It's because we started t at 0. If we wanted to graph the other quadrant, we could change this t min to a negative value. We get a lot more of our tangent line graph, but also remember, you'd also be generating something different with your original polar graph. So another strategy is you might just make x3 of t and y3 of t. Just make these x2t of negative t and x2t of negative t, and it would graph a corresponding part of the line in the third quadrant there.
Cool.
All right. Before I turn it back over to you, Steve, I mean, we can do, acceleration, speed, those integrals, but they're really just like you would do those kinds of things. You'd just be referring to these functions and doing a DT,
Uh-huh.
and it works just fine. But I want
One
to
thing,
leave you plenty of time to do the next problem. So
one thing perhaps before we leave this, Tom,
sure.
would you just show on the 84 how to get a second derivative? For example, find the second derivative of x at 2.
Okay, sure. All right.
Because
So
that's just a little tricky.
so the second derivative of one of the components,
Yes, please.
like the acceleration. Okay.
Yeah. Yep.
All right. So let me see. Okay, I'll just kind of do it from scratch, I think, here. I'll just
Okay.
do a derivative with respect to t. Let's do the x1 of t
Yeah,
again.
that'd be great. Yeah.
And I think I've actually, that wasn't really what I wanted to do. So let me try again here. So I'm going to delete that. I'm taking the derivative of a derivative. So I think I need to do the next derivative in here. So let me go back to the math menu and pull up the derivative again. So we're doing a derivative of a derivative. Now I'll do my x1 of t.
Okay.
My apologies for getting a little ahead of myself here. Okay. And on this inside function here, I'm just going to put a t.
Okay.
Because I want to think of this is a function of t. So this is the first derivative of the x component. So this is my velocity function.
Mm-hmm.
And then I'm taking the derivative of that and evaluating that at 2. Or wherever. I think, was that where we were evaluating?
I believe so. Yes, Tom.
Okay. Yeah. And hopefully this will give us the value that we were looking for.
Beautiful.
So good.
Very
I think
cool.
the tricky part here is you don't want to put a 2, t equals 2 inside this innermost parentheses, because that's going to evaluate to be a number. And then when you take the derivative of that, you should just get 0.
Mm-hmm.
So we really need to write, it looks kind of funny, this t equals t, but that's maintaining that as a function. And then we can evaluate the derivative of it at a specific value with the numerical derivative. So it works very fine.
Cool.
Okay, anything else?
That's good, Tom. That's really neat.
Okay. Anything from the chat, Curtis, that you see, or things look good? All right, I'll stop sharing, Steve, and turn it back.
Nothing in the chat right now.
Okay. All right. Back to you, Steve.
All right. Thank you, Tom. Okay, so in problem number 2, we're going to switch to polar coordinates here. We're going to look at a polar function, r, that's defined to be 2 plus the cosine of 3 theta divided by 2. We're going to look for values of theta between 0 and 4 pi. And the very first skill here is simply getting a sketch of this polar curve. And so I have done this 2 ways. I've actually done it on the left-hand side with the TI-Nspire. And again, as Tom was saying, you can switch between these modes between, say, y equal, a function mode, parametric, and polars. So it's actually kind of easy to do this. And although I did not put a screen illustration in here, on my page 2.1, I actually defined r of theta to be this function. And so then when I went to the graph screen, my R1 is r of theta. And boy, that's kind of a different looking curve, isn't it? I don't know what you call that, but that's a different looking curve. And on the right-hand side, I did something a little different. I don't know if I've seen these kind of graphs too often. But on the right-hand side, what I did is I sort of superimposed a polar grid. And it might be a little hard to see on my screen, but I superimposed a polar grid with a rectangular grid. Because often when we're graphing these, we find the x and the y coordinates associated with this polar function. And so sometimes it's easier, at least for me, to have both of those grids there. So that's what it looks like. I don't have a description for that. It's not really a 3-leaf rose or anything. But I believe that's a complete graph from theta equals 0 to 4 pi. So how about that? All right. Let's see if we can do a little bit with this function. And we're going to run into an issue here with the TI-Nspire that Tom and I have talked about frequently. And one where you just have to be very careful about what technology gives you back, returns as an answer. So the first one, find the slope of the tangent line to the graph of this polar equation where theta is equal to pi over 6. Well, okay, look, I've got to think about what the equation is. dy dx is the derivative of y with respect to theta over the derivative of x with respect to theta. And remember these two equations here. So thinking a little bit about what's to come here and trying to make this a little bit logical and easy for me to understand, I actually defined a function in my TI-Nspire for the numerator, num of t, which is looking at this equation, the derivative of r with respect to t times the sine of t, plus r of t times the cosine of t. And you know, you're absolutely right. I know Curtis is going to ask me, well, why didn't you use a theta in there? And I could if I really wanted to, but I find it much easier to type with a t standing for theta rather than using the actual symbol theta, but could if I wanted to. Here's the denominator, dr d theta times the cosine of theta minus r of t times the sine of theta, and then to find the slope of this tangent line, it is the numerator at pi over 6 divided by the denominator of pi over 6. And you'll notice here I used my common trick of multiplying by a 1 with a decimal point after it, because otherwise I believe the Nspire will come back and give me a symbolic or analytical solution to this. And I want to see the numerical value. It's minus 0.798. Now, that's the slope of the tangent line, but I wanted to see some visualization of this, some way to kind of back this up. And I apologize, Tom, I may need some help on this one, but I think what I was able to do was on the TI-Nspire, I was actually able to draw a tangent line to the curve at the point where theta is equal to pi over 6. I was actually able to name that value of theta. And it not only does it draw in that tangent line, but it gave me the equation of that tangent line down here, and I can see the slope, and it agreed pretty closely with that one over there, the one that I got. So I feel very good about this. Not only does the tangent line look correct, but I've got a corresponding slope on the graph screen that corresponds with the one that I got on the calculator screen. I feel pretty good about that. Okay. There's an awful lot going on in this page. Holy Toledo. Let me see if I can decipher all of this. Find the points on the graph of the polar equation where the tangent line is horizontal or vertical. Holy Toledo. Horizontal or vertical. Okay, let's think about this. Remember that I have my two functions, num and den, for the numerator and denominator corresponding to the slope. Well, where is the tangent line going to be horizontal? It's going to be horizontal where the numerator is 0 and the denominator is non-zero. Where's the tangent line going to be vertical? Where the denominator is 0 and the numerator is non-zero. So let's work sort of back and forth here between some screen illustrations on the left-hand side. So let's see, the very first thing I wanted to do is to find out where is the numerator in that slope equation, given up top there symbolically. Where is that 0 for t between 0 and 4 pi? Well, Tom knows I like to use this zeros, built-in zeros command in the TI-Nspire. And again, the reason for that is because it puts these values in a list, and it puts them in a list that I can then refer to. So I can go grab an element of this list to a great degree of accuracy, and I really like that. So let's see, I got 4 values there, and I apologize for this, Curtis. My screen illustration is going to get a little messy here, but let's see. That sort of suggests here that there are 4 places where there's a horizontal tangent line. Now, I don't know if you can see this on your screen, but on the bottom left-hand screen illustration, there should be 4 green dots there where it looks like there's a horizontal tangent line. So let me see if I can find them. I think there's one here. It looks like there's a horizontal tangent line there. There's one there. It looks like there's one there. And it looks like there's one there. I'm feeling pretty good about that. I don't see any others on that polar curve. I don't really think there are any. I feel good about that answer. All right, now I'm going to shift a little bit over to the top right-hand screen illustration. I'm in a lists and spreadsheet page. And what I did was I converted the polar coordinates into rectangular coordinates. So let me see if I've got this right. So for theta, or t, equal to 0.961, here's the x coordinate and there's the y coordinate. And let me just do this with one value and see if this works. 1.219, 1.745. Yep, there it is. There's my 1 point on the polar curve where the tangent line is horizontal. Looking pretty good. And I did that for those 4 values of theta or t. Cool.
Got a question for you, Steve.
Shoot, Tom.
All right. Well, you mentioned that if the numerator of your derivative there is 0, but the denominator is not 0, you got a horizontal tangent. And vice versa, if the denominator was 0, but the numerator was not 0, you'd have a vertical tangent. What if they're both 0?
Boy, that's a good question. Maybe we should put that in the chat or ask Curtis.
Why are you laughing?
I think
We're
we should
laughing with you, Curtis.
put that one in the. I think that's a good one for the chat. That's a good one for the chat, Curtis. What happens if both the numerator and the denominator are 0 at one specific value of theta, or in my case, t? Okay.
Sounds
Okay. So while you're thinking about that, now what happens when I find the places where the denominator is 0? So when I was investigating this, when I was thinking about this, I guess the very first thing I did was I looked at my curve. And if you can see this on your screen, there are actually some bulleted points. There are some points on the curve. I think they're kind of red. They've got a red circle there, but it's an open circle. So I think here I've got one over here. 1, 2, 3, 4, 5. It looks like to me when I did this that there are 6 places where the tangent line is vertical. So let's see. I found the zeros of the denominator. Let me count them up. 1, 2, 3, 4, 5, 6. Oh, I must have them all. But wait a minute. What's true about that first one, which is 0, and that last one, 12.566? What's true about those 2 values of theta? One of them, of course, is 0, but what's another way to write that 12.5666? That's actually 4 pi. And so those 2 values of theta actually correspond to this value, or this point, excuse me, on the curve where the tangent line is vertical. So what happened here? It turns out that the TI-Nspire misses one of these values of t. Now, we're not sure exactly why that is, but it does. And that's why you have to be very careful about what technology
Hey,
returns.
Steve,
Yes.
when you were doing that, what was your what were the parameters you had for t, or sorry, theta in this case? 0 to 2 pi?
No, on the end here, I think I have t between 0 and 4 pi.
Oh, 4 pi. Okay.
Okay.
Hmm.
So,
I just wondered if that was a fence post thing and it was, that symbol, that arithmetic adding. So if you had had it from 0 to say 5 pi.
now that's very interesting because I believe that there was one point that it missed, one value, excuse me, that it missed. And with a little bit of thinking about this and a sketch of just the denominator over here on the right-hand side, just a regular old sketch of the denominator evaluated at x suggested to me that there was a value around 5.57, which is in here, I believe, where it does indeed equal 0. So I went back and I tried zeros again, but restricted my value of t between 5.4 and 6, and son of a gun, I found that remaining value. I think that sixth value of t. So very interesting. I'm not sure exactly what's going on in the background. I'm not sure of the numerical algorithm used to find these zeros. But we've run across this one or two other cases, I think, didn't we, Tom?
Yeah, I think so. It's
We saw this one or
one
two
we're
other
still
cases.
cogitating on.
Yeah, mostly dealing with trigonometric functions, I believe.
Yeah. Well, I think this really underscores how important it is to graph because this
Yeah,
is
exactly.
really, really helpful
Yeah.
accounting for all the places where we
Yep.
could be finding
Yep.
it.
Yep. I
And
think
so
that's good.
what I did on the list and spreadsheet page, and you can't see them all, only 5 of them here, but I did the same thing where I found the X and the Y coordinate and Cartesian coordinates here. And they do correspond to my points 1, 2, 3, 4, 5, 6. There are 6 places actually where the tangent line is vertical. Now that's a neat problem. Curtis, any answer yet to our question about what happens if both the numerator and denominator is 0?
Mark Corelli and I, of course, were talking about the fact that that'd be considered indeterminate, right?
Yes.
And Mark suggests that maybe there's a possibility we could explore with good old law hospital.
L'Hopital's rule, perhaps. Yes, absolutely.
Mhm.
Absolutely. Yeah, you might have to take a look at a one-sided limit. The limit could be different from both sides. Absolutely. Very good. Excellent.
So another question came up in the chat just now for 2C.
For
Uh,
2C,
the problem asks for 2 points or for the points. Does the answer need to include both coordinates is the question.
yeah, it says find the points on the graph of the polar equation. Yeah. So my points are over here in this list and spreadsheet page. So I didn't write them all out specifically, but yeah, they're all over there in my list and spreadsheets page. Yeah, I'm really not asking for the values of t here, but rather I'm asking for the x and y coordinates.
So another suggestion that popped up in the chat as
Yes,
well was, is it a good idea? It seems like it is possibly to graph both the numerator and the denominator separately in
excellent.
function mode.
Excellent idea. Yep. Sure, that's what I've got down here in the bottom right-hand side, which helped me determine that, you know what, there was this sort of missing value of t. Absolutely, Curtis. Great suggestion. Yep. Very good. And in fact, Tom showed us, I think last time we were on, Tom showed us how to find a 0 and showed us how to store that value in a variable back on the calculator screen on the 84. So yes, that's another way you could do it analytically. Yep. Pardon me, numerically. Yep. Very cool. Tom, you want to do anything with this one?
Sure, Steve. That'd be fine.
Okay. Okay. There you go.
Okay. So I'll share my TI-84 screen again. Let's see. Hopefully that's come up. Okay, great. Can Okay, well, we were working in parametric, but Steve has switched over to polar. So let's go back to our mode again. And I'm going to go down to that same line where we had function and parametric. This time I'll go all the way over to polar, hit enter. And now when I go to my y equals screen, I see, oh, there happened to be a polar equation in here already. Let me go ahead and clear that out. And you might see there's something kind of interesting here beside R1. I think I'll leave that there. That's a kind of type of graph you can make. We'll see what it does when we graph this. But let me go ahead and put in the graph Steve was working with, which was 2 plus the
Nope.
cosine.
Oh, yeah. I'm sorry. Sorry.
Yeah, I got the right one here, I think.
Yep, you're right. You're good.
And then it was 3 times theta. Well, now that we're in polar mode, that xt theta key is a theta key. So I'll press that key. There's a nice theta for us. And we're dividing by 2.
Mm-hmm.
All right, so there's my polar function. And if I go to the window, oh, again, things have changed. My x-min, x-max, y-min, y-max are the same as they were when I was working, the last thing I was doing with that parametric problem. Those might not be the best. Let me leave them for now. But I notice that you've got a theta min and theta max. I think Steve went from 0 to 4 pi. So let me go to theta max and actually put in 4 pi. And when I hit enter, it will convert that to a decimal. The theta step here, not quite sure what that is. I think what I'm going to do, I'm going to put in pi over 24. That's would give us some nice multiples of pi. Okay. Oh, that number looks familiar. I think we saw that in the window menu when we first entered. And now I've got x-min, x-max, but I think right now I'm going to do zoom. And I'll just do zoom decimal. That'll get me back to my original.
How about
And
that?
if you notice that it was actually drawing it as we went. So that was a special kind of graph setting that I had. If I go back to y equals, what you can do is if I arrow over to that area just to the left of R1 and hit enter, it gives me a chance to choose a color for my graph, but also a kind of a style for the line. And I'm just going to go ahead and put this on its regular kind of thick mode there. Go okay. And then when I graph again, boom, it just graphs very solid. But I kind of like that moving ball thing because it gives you a sense of how it was moving as theta was increasing. So this looks like a new, pretty good graph. The window's actually pretty good for this.
Yeah,
right?
yeah.
One little thing I'll show folks that they might like to use, people who know me know I'm not a huge person for programs, but there's a few that I really do like to have as utilities on my 84. And one of them is for polar. Steve had a picture where he had overlaid a kind of nice polar grid. And I've had a lot of people ask me, well, can you get any way to get a polar grid on the 84? And I've written a little program that does that. So let me go to program here, to TI Basic. And you're going to see 2 programs that have polar in the title. One is polar grid. That'll overlay this kind of gray polar grid with radial lines and concentric circles. Polar off just erases that. So because that grid will stay there until you, even if you go to function plotting, that thing will be there until you erase it. So that's what polar plot off does. So I'm going to execute polar grid. And then if I go to the graph, we can see there's a nice polar grid there, and my same polar function is there. And I know we're about out of time, but if I go on to trace, you're seeing, you might hardly be able to see it. It's actually showing that I use a scatter plot to create a connected scatter plot to make this polar grid. So let me hit a up arrow. There's my
Oh, there you
polar
go.
function.
Mhm.
And you notice it's giving me the theta value and the X and Y values as I trace around the polar curve. If you want to see the polar coordinate, well, we have one of the two polar coordinates. We have the theta value. We want to see the R value. Where you would go is the shift of the zoom key. So second zoom is format. See at the very top there, it says rectangular GC. That's graphing coordinates. If I arrow over to polar graphing coordinates, hit enter, and then return to my graph and hit trace. Now it's tracing in polar coordinates with my R and my theta there. Okay.
So Tom, because your theta step was a multiple of pi, this actually helps you, I think, really see, where that polar point gets plotted, right? For certain
Right.
values for
And
theta.
these grid lines are deliberately placed. I think these are pi over 12.
Yeah.
So this second one's pi over 6. The third one's pi over 4, right along the diagonal. That makes sense.
Uh-huh.
I think it would be pi over 6 would have been, let me trace back. There we go. That'd be about pi over 6.
Yeah.
Let's think about that. Pi is a little bit over 3. So pi over 6 would be just a little bit over 5. Okay, that's
Yeah.
making sense. And notice it's right on that
Yeah.
grid line.
That's really cool.
Yeah.
I mean, this
But I
would
like
help.
this polar grid, especially when I'm first doing polars with students. I think it helps them keep track of what's going on.
I don't know if this happens or not, but could you trace just a little bit more to see if there's a value where R is negative?
Sure. Okay. So we'll
I'm
keep
not sure if that
tracing.
happens here or not, but I thought it did.
So far, let's see.
So far it isn't, but keep going.
Well, Steve, I'm going to
Yes.
guess it can't happen.
Oh, why? I wonder why that is.
Well, I'm looking at your formula here,
Yeah.
and I'm thinking, well, the cosine is always
Gotta be
between
between.
-1 and 1.
Yep.
So if you add 2 onto it, you'll always be between 1 and 3,
Yep.
right? So,
Pretty
and that's
cool.
what's playing out here. And I'm
Yep.
sorry if I stole a punchline you were trying to make.
No, we set that up very well, I think.
Okay. Yeah, so these R's are all positive. But
Yep.
yes, you can have lots of polar functions where if the R is negative, it's reflected through the origin. It'll
Yeah.
end up on the
Pretty cool.
opposite side of where the polar ray would be. Okay. Real quickly, I'm going to go back to program and do polar off. And then when I go back to the graph, the polar grid is off.
Gotcha.
And I think, Curtis, if you can be so good as maybe you can make these programs available when you post.
Oh, I suppose.
All right, I'll stop and share because I think
No, that's all right.
Okay.
I already made the folks aware that I would be definitely doing that.
Okay, great.
Okay.
Making those programs available along with the solutions. So I will post the solutions tomorrow. I know there were a few teachers that tried to log in and use the questions earlier last week, and I failed to get them up there in the YouTube description. So my apologies if you logged in looking for those and couldn't find them. If you ever do that, just send me an email, same location that I post every week for the certificates. So tonight we are going to have the certificate available. You can shoot me an email, curtis@ti.com. I'll put that in the chat, and that way you can send me a quick email to get your professional development certificate. along with I'll also send back the programs and things of that nature. So one thing before we sign off tonight, Steve, Tom, Allison did stop by check in on us. So
Oh, good.
she sends her well wishes. So excited to have her. So hey, thank you everyone. We will sign off and we'll see you for our last session coming up on April the 17th. No, that's
Yes.
pre-calculus.
That's pre-calculus, right,
24th,
21st.
21.
20,
21.
21st.
Yeah.
21st is our last Monday night calculus session of the season, getting the students ready for that AP calculus exam in early May. So one last session here in a couple of weeks. We'll see you then.
Very good.
Bye, everybody.
Okay. I think we are off, guys.
Very good.